we'll go to the PowerPoints and see what we have for today. So today I'm going to talk about quantum physics. That's basically the first lecture that we are going to have about quantum physics. Uh, the idea is that in the next 4 lectures, I will cover different topics in modern physics, mostly related to quantum physics. They are very basic ideas, but they are very interesting at the same time. Sometimes some students become interested in these new ideas, and then they decide to take more advanced courses. So in future, if you want to do that, I have a course called Modern Physics. It's not offered every year, but whenever I offer it, you can join that course and learn more about these materials. Now, again, let me tell you that I skipped a very interesting uh, part of this course, which is about a special relativity. That usually takes 2 lectures, but it's not as important as quantum physics for some of you guys, especially those of you who are doing chemistry. So in the video that you watched before this lecture, I talked about a specific phenomenon where classical physics failed to explain the outcomes of a certain experiment. That experiment was black body radiation. So physicists had realized that if they plotted the intensity of the emitted light or emitted electromagnetic waves from black body objects, the shape is something like this, as you can see. Uh, so there is a peak, there is a certain wavelength that the intensity of the electromagnetic waves, emitted electromagnetic waves at that certain wavelength is maximum, but you get basically all possible wavelength. And then they had realized there is a relation between the temperature and the maximum wavelength, and that relation is this, what we call Wien's displacement law. You can actually write it in terms of wavelength. Lambda max is this specific number divided by the temperature, or if you want, you can use the fact that lambda is c over frequency, where c is the speed of light, to actually find the relation between the frequency of the peak, the frequency here, and the temperature. This was an experimental result, but using classical view of electromagnetic waves, where we considered electromagnetic or light or anything else actually were waves, couldn't explain this result. And as if you remember, as I mentioned, if we wanted to do actually if we wanted to use the classical view to explain what is happening, the curve should look like this, which is going to result in a catastrophe, because it would go to an infinite amount of energy. In other words, the black body had to emit infinite amount of energy, which is not correct. But in 1900, Max Planck actually assumed that light, or radiation in general, was not exactly wave. It was made of small packages of energy, and each package of energy assumed to have a certain energy which was related to its frequency. So that package's energy was h times f. So if you have just one package of energy in the electromagnetic wave or in radiation, the energy of that package would be this h, which is a fundamental constant of nature. It is called Planck's constant, times the frequency of the wave associated with that radiation. And once you have the energy for one single package, if you have n of those packages, then the energy of the entire wave becomes n times h times f. Now, before moving forward to a different experiment that scientists couldn't explain using classical view of electromagnetic waves. Let's do a simple example here so you see how we can use that displacement law to find to answer some questions. So we have an infrared thermometer that detects radiation emitted from the surface to measure the temperature. So a physician measures the patient's skin temperature to be 34 degrees Celsius. The question is, what is the wavelength of the photons emitted with the greatest intensity from the patient's skin? So you basically want to you want to find a lambda maximum, lambda for the peak. There are different ways to do that. I actually have done it the long way here. So what I can do, first I will use the equation for the peak frequency to find the peak frequency. Well, the only thing that you have to be careful here is that this T, which is the temperature, must be in Kelvin. And while I'm thinking about it, I realized that I made a mistake while I was doing this. So if you want to convert Celsius into Kelvin, you have to add this number to 273, if you remember. That's how we converted, how we went from Celsius into Kelvin. And I believe I made a mistake when I did that in my calculation. So let me go back and fix it, because 34 plus 273 is going to be 307, right? So I may have done it as like 297. So I have to change this to 307. And then this number will change to a smaller value, which is probably 945. So anyways, I'm sorry about that. Let me go back. So the temperature in Kelvin is 307. You multiply it by this number, and then once you have the frequency, you can use the equation for a wavelength, which is the speed of light divided by the frequency. The speed of light is 3 times 10 to the 8th meters per second. You divide it by this number, and you get the wavelength of the maximum intensity. Now, do you guys have any question about black body radiation before I move on to the next experiment? I have a question. Let me go to, yes, Tim, what is your question?
That number in front of the F peak, the 1.01352 times 10 to the 11th, is that
Yes.
some other kind of constant?
I mean, it's basically that constant that we had in back here. That's, I mean, if you look at the displacement law that I talked about in the video you watched before this lecture, I had
Right.
it in this form. You do remember it was lambda max times T equals to this number, remember?
Yes.
Now, if you replace lambda maximum by C, which is the speed of light divided by frequency, then you are going to get this number. That number is basically the speed of light divided by this number.
Okay.
But you shouldn't be worried about these numbers. You are going to get either of this one or the other one in your formula sheet. So it's not something that you have to be worried about. But these are not fundamental constants of nature. A fundamental constant of nature is like the charge of the electron, or this Planck constant. This is a fundamental constant of nature, which is a very, I mean, if you go anywhere in the universe, physicists believe that the Planck constant is going to be this. That's why we call it the fundamental constant of physics. Okay. Now let's talk about a different experiment, which is called a photoelectric effect. This is an experiment that was done towards the end of the 19th century. There are two plates made of metal, so they have free electrons. And scientists realized that when electromagnetic waves strike this plate, electrons are ejected from this plate. As a result of the electromagnetic waves hitting this plate, electrons were ejected, and they could be detected on the other side if they created some kind of voltage between these two plates. Once they observed this, they tried to use the classical view of radiation to explain what happens in this experiment. In other words, they try to use those classical views to explain the results of this experiment. Now, let's see what the classical view of radiation is. The classical view of radiation is this, that if radiation is made of waves, electromagnetic waves. And we have talked about this in the previous chapters, that these waves carry energy, if you remember, because they are made of electric field and magnetic field, they have energy. So you can say when these electromagnetic waves strike this surface and they are absorbed by this surface, they give their energy to the surface. And then there are free electrons with very little binding energy to the surface. When those electrons capture the energy, when the energy becomes more than their binding energy, they can use that energy to get rid of the surface, to escape the surface. So this is the way that physicists try to use classical view of radiation to explain what is happening in this experiment. These electrons that are ejected are usually called photo electrons. Now note that electrons have a negative charge. So when they are ejected, if you create some kind of potential difference between these two plates, if this is connected to the positive terminal and the other one is connected to the negative terminal, once they are ejected, actually they are going to accelerate towards this one, and then you are going to see some electric current in this circuit. So you can measure the electric current here. But at the same time, if they are ejected, they are going to have some kind of energy. I'm going to talk about that kinetic energy shortly. They are going to have some kind of kinetic energy. And as a result of that kinetic energy, even if you don't apply any voltage here, but if you create some kind of vacuum in the tube, those electrons can reach to the other side because they come out of this plate with some kind of energy. Now, if you reverse the polarity of this power supply, in other words, if you make this one negative and if this one positive, if this becomes negative, then the electrons are going to be repelled by this one. So while after they are ejected and they are moving this way, but as a result of the repulsive force, they are going to slow down, and eventually they are going to stop, and some of them might even stop before getting to this the other plate. So there is a certain potential that you can apply here that makes all the photoelectrons stop before getting to this other plate, and as a result you wouldn't see any electric current in the circuit. That is what we call the stopping potential. But before that, let me tell you what the experimental results were, and see if the classical view of radiation can explain those experimental results. You probably can guess that those classical views or the classical description wasn't able to explain the result. So I have a list of different things that is happening here. So let's see. As I mentioned, electrons are ejected. As I mentioned, electrons capture the energy. Electron needs to capture some energy in order to be able to overcome the binding energy that keeps them in the metal. Different electrons have different binding energies. The ones with the smallest binding energy need the smallest amount of energy to be ejected. Now that minimum energy for a certain metal is called the work function for that metal. So the work function for a metal is actually the minimum binding energy for the free electrons inside that metal. And that is the minimum amount of energy one needs in order to make sure that at least one electron is ejected from the surface. Now, when the electron receives the energy from the radiation, part of that energy, if the electron wants to be ejected, the energy must be greater than its binding energy, or at least equal to it. Now, if the energy is more than the binding energy, electron is going to use part of that energy to get out of the surface, and the rest of that energy is going to become its kinetic energy. It's just an example that I'm trying to tell you. Let's assume that the work function of a let's not talk about work function yet. Let's assume the binding energy for an electron is 10 electron volts. That means that a specific electron needs 10 electron volts to overcome the binding energy and escape the surface. Now, if that electron captures 15 electron volts energy from the radiation, it can use 10 out of that 15 to escape the surface. Now it has 5 electron volts energy more, and that 5 electron volt energy is going to become its kinetic energy. So the kinetic energy of the electron or the photoelectron is going to be the energy that the electron captures from radiation minus the amount of energy that it has to spend to actually escape the surface. Now, if all the electrons capture the same amount of energy, the ones with a smaller binding energy are going to be ejected with more kinetic energy. The ones with the smallest binding energy are going to have the maximum kinetic energy. So if you want, you can say the maximum kinetic energy for the electrons would belong to those electrons with the smallest binding energy. And if you remember, the smallest binding energy is what I called the work function. So these are some of the things that we need to know, but let's see what the experiment tells us and what the wave theory of radiation predicts. So I have a table for you, 4 predictions by wave theory, and if the observation actually confirms those predictions. The first one, photoelectric effect should occur at any frequency, because as I mentioned, the electrons capture the energy from the radiation, and the energy of the radiation basically depends on the intensity of the radiation. So if you wait enough, it doesn't matter what the frequency is, the electrons are going to accumulate enough energy, which is more than their binding energy, and as a result, they are going to be ejected. Observations didn't show that. Observations show that for any certain metal, there is a specific frequency called the cutoff frequency, that if the frequency of the radiation is less than this cutoff frequency, no matter how much the intensity of that wave is, no photoelectron is going to be observed. Again, according to the wave theory, frequency shouldn't matter. If you have a very high intensity wave, it has a lot of energy delivering to the surface, and electrons should eventually get enough energy to be ejected. But In the experiment, for any metal, they found a certain frequency. They called it the cutoff frequency, and below that frequency, no photoelectron was emitted, regardless of how intense uh, the uh, the wave was, or the intensity was. The other one, the other prediction, if you increase the intensity of the light or the wave, that means you are giving more energy to the electrons. Electrons spend a certain amount of energy to uh, escape the surface, but now they have more energy, so their kinetic energy should increase. That was the prediction of the wave theory. Experiment showed that maximum kinetic energy was not dependent on the intensity of the light. The wave theory didn't predict any kind of relationship between the energy of the photoelectrons and the frequency of the radiation. But observation showed that if you increase the frequency of the uh, radiation striking this surface, the maximum kinetic energy of the photoelectrons will increase. And then the final prediction for wave theory was this, that if you have even low intensity light, if you wait enough, at some point the photoelectrons are going to be released. At the same time, if you have very high frequencies, let's say above this cutoff frequency that I talked about, but with very low intensity, wave theory predicts that you have to wait for the electrons to actually capture enough energy if the intensity of the incoming light or incoming radiation is low. But experiments showed that even for very, very low intensities, as long as the frequency was above the cutoff frequency, once you started the experiment, immediately, almost immediately, these photoelectrons are ejected. So 4 predictions that wave theory had, none of them were confirmed in the experiment. So that tells us that the classical view of wave probably is not the best way to describe this experiment. Another thing that a scientist or physicist actually observed was a relation between the stopping potential and the frequency. They realized that if they change the intensity, you increase the intensity, the current that they receive here is going to increase. That's actually something that classical theory can explain, because more intensity means more energy for the electrons, so electrons would go faster, so you have more current. But at the same time, experiments showed that the stopping potential, which is related to the maximum kinetic energy of the photoelectrons through this equation, doesn't depend on the intensity. It doesn't matter how much intensity you use for the light, the stopping potential, as well as the maximum kinetic energy that the photoelectrons have after they are ejected, doesn't depend on the intensity. It just depends on the frequency, as I mentioned in the previous slide. Now, how can we explain these outcomes of the experiment? Believe it or not, the person who actually came up with an interesting idea was Einstein. In 1905, Einstein actually used the idea of packages of energy to explain what happens in the photoelectric effect. Einstein also discovered a special theory of relativity that we didn't talk about, but the reason that Einstein received a Nobel Prize was this photoelectric effect. So the proposition that he had was this. He said, light in this experiment doesn't act like a wave. In this experiment, in photoelectric experiment, light acts like it's made of very small particles. He called them photons. And these photons are very small, massless particles that move at a speed of light. And instead of calling them, basically, instead of calling them the packages of energy, he called them photons. But the energy of each photon is still h times f, Planck's constant times the frequency of the wave associated with these photons. And if you want, you can replace f by c over lambda. C is the speed of light, and that's the wavelength. So this is what he proposed. He said in this experiment, light doesn't act as a wave. It acts like it's made of small particles. Now, so that's a stray of particles heading this surface. If a photon is captured by an electron, it delivers its energy to the electron. So just one single photon hits one electron, and then the electron captures that photon and its energy. Now, if this energy is more than the binding energy of the electron, then the electron can easily use that energy to escape. But if the energy is less than that, as a matter of fact, that photon is not going to be captured by the electron at all. There is no chance that the electron is going to capture the photon with energies less than its binding energy. Now, if you have an electron capturing a photon, if the energy of the photon is more than the binding energy, the electron is going to be ejected. The kinetic energy of the electron is going to be equal to the energy of the original photon minus binding energy of the electron. And then those electrons with the smallest binding energy, the quantity that I call the work function, are going to have the maximum kinetic energy. So you can say maximum kinetic energy for the photoelectrons is going to be equal to the energy of the photons, which is HF, minus the work function for the metal. This is how Einstein actually tried to solve the issues that physicists had with photoelectric effect. And you can see that these propositions immediately solves all of the problems that the classical theory had. So let's see. Observation says that no electron is emitted for frequencies below the cutoff frequency. Well, the explanation with using the Einstein theory. If you want to have photoelectrons as a result of absorbing a photon, the photon's energy, which is HF, has to be greater than or at least equal to the work function. Now, from here, you can find, if you divide both sides, I mean, that's HF divided by, I mean, HF is greater than phi, then you divide both sides by H. So you have a formula that says F has to be greater than phi divided by H. And phi divided by H is going to be the cutoff frequency. If the frequency is less than that, the energy of the photon is just not enough for any electron in the system to escape the surface. Second observation, kinetic energy maximum is independent of light intensity. As you saw, that kinetic energy actually just depends on the frequency of the wave. If light frequency increases, kinetic energy of the photoelectrons increases. How can we say that? Well, if the frequency, I said intensity, if the frequency increases, the kinetic maximum kinetic energy is going to increase, and that should be obvious from this linear relation that we have between maximum kinetic energy and the frequency. If you increase the frequency, the maximum kinetic energy will increase. And then electrons are emitted from the surface almost instantaneously. That wasn't the prediction with a classical view, because if the intensity is very low, we have to wait for those electrons to capture enough energy. But in this view, electrons don't have to wait. As long as there is a collision between a photon and an electron, as long as that photon has enough energy, more than the binding energy, the electron is going to be ejected. So we are not going to need to wait for the photoelectric effect to happen. So this is the basic idea. Like I said, the minimum energy that photons need to have is the work function. Work function is a property of each metal. Different metals have different work functions. They are at the order of magnitude of the work function is electron volts. I don't know if you guys remember electron volts, but electron volts is a unit for energy that we usually use in atomic physics. 1 electron volt is 1.6 times 10 to the negative 19th joules. That's basically the charge of the electron. So 1 electron volt is 1.6 times 10 to the negative 19th joules. Okay, then as I mentioned, the kinetic energy, the maximum kinetic energy is linear in frequency. So if you want, the equation is HF minus phi. So that's the equation for the maximum kinetic energy. Now at the point where this line hits the horizontal axis, the kinetic energy is 0, and that is going to be the cutoff frequency for us. So you can actually find the cutoff frequency to be the work function divided by h, or you can find the cutoff wavelength by replacing frequency and c over frequency by c over lambda. One interesting thing that I should mention here is this, that if you use a different metal to do the photoelectric effect, you are going to get a different line, but the slope of that line is going to be the same. Because if you look at this equation, the slope of the line is h, and it is not dependent on the type of metal that you are using. So all of the metals that you use in the photoelectric effect, they are all going to have this to give you the same slope. But then the intercept that they have with the horizontal axis is going to be at different locations, because that is going to tell you what the cutoff frequency is, and the cutoff frequency is going to depend on the work function. Different metals are going to have different work functions. One other thing that I should mention is usually the work function is given in electron volts, but when you multiply H and F, if you use the standard unit, H is 6.63 times 10 to the negative 34th joule second, and frequency is of course in hertz, then the unit for this one is going to be joules. So if you want to use these two in the same formula, you have to make sure that they have the same unit. Either convert this one into electron volts or convert this one into joules. Okay. Now I'm going to ask you some questions to make sure that we actually understood everything that went on today. So let me bring up the Nearpod app and ask you to join by putting the code NRQJD. NRQJD. The first question is just about a photon. The question is, which has more energy? A photon of red light, yellow light, green light, or blue light? Okay, well, the formula that you have to use is basically equal to H times F. The one with the highest frequency is going to have the most energy. Uh, red light actually has the smallest frequency and the longest wavelength. Blue light has the highest frequency and the shortest wavelength. Blue light actually is the most energetic among all of these, and red light is the least energetic photon. So the correct choice is D. What do you think about this one? The cutoff frequency for light in the photoelectric effect for metal B is greater than that of metal A. Which one has a greater work function? Remember the relation between the work function and the cutoff frequency. H times F cutoff was the work function. I think I have the formula here for you. Okay, so in this problem, metal B has a greater cutoff frequency. So FC is greater for B. And since phi is proportional to F, that means metal B is going to have a greater work function. So the correct choice is B. Next question. A metal surface with work function phi equals to Hc over 550 nanometers is struck with blue light and electrons are released. If the blue light is replaced by red light of the same intensity, what is the result? You have to be careful while you are giving the answer to this question. Okay, let me go to the next question, but here if I want to answer this question, based on the formula that I gave you in the previous slide, if I go back here, the work function is hc over lambda cutoff. So basically you can say the cutoff wavelength is 515 nanometers, maybe something around here, right? So that is the cutoff wavelength. Now note that wavelength and energy of the photon are inversely proportional. So if you move in this direction, the energy of the photons will increase, while if you move in this direction, the energy of the photons will decrease. So if you are illuminating the surface of the metal by blue light, you're actually providing the surface with photons which have more energy than the minimum required energy to eject photoelectrons. And that's why you see electrons are released. But if you use red light, which is in this area, the wavelength is longer than the cutoff wavelength. In other words, these photons do not have enough energy to release any of the electrons in the surface. So in this case, no electron is going to be emitted because the photons associated with red light do not have enough energy to overcome the binding energy even for those electrons with the smallest binding energies. So the correct choice here is D. What do you think about this question? A metal surface is struck with light of lambda equal to 400 nanometers. Now, if the 400 nanometers is replaced by 370 nanometers with the same intensity, what is the result? Okay, very good. So let me explain what the answer is here. Note that the intensity of a light is going to tell us how many of the photons we have in the light, in the beam, in the radiation. So if you don't change the intensity, that means you're not changing the number of incoming photons. But by reducing the wavelength and using the fact that the energy of each photon is h times f, or hc over lambda, you can say that the energy of the photon is inversely proportional to its wavelength. So by reducing the wavelength, you have increased the energy of each individual photon. The number of photons is the same, but energy of each individual photon has increased. So when there is a collision between a photon and one electron, more energy is captured by the electron, and since the amount of binding energy for each electron is constant, but it has more energy now, the electrons that are emitted are going to be more energetic. So the correct choice is going to be C. What do you think about this one now? It says you are increasing the intensity without changing the wavelength. So basically, you are not changing the energy of each individual photon, but you are increasing the number of incoming photons. What do you think is going to happen? Very good. Several of you gave me the correct answer for this question. Uh, if the intensity, if the wavelength is the same, the energy of each individual photon is going to be the same, and each photoelectron is going to capture the same amount of energy as a result of the collision. So the energy of individual electrons is not going to change. But since we have now more photons coming in, there is going to be more collisions between photons and electrons. More electrons are going to be hit by these incoming photons, and as a result, more electrons are going to get enough energy to escape the surface. So you are going to see more electrons emitted in a given time interval. So the correct choice is going to be A. Now let's do a simple numeric problem before finishing this lecture. Electromagnetic wave with frequencies ranging from 4 times 10 to the 14th hertz to 7.9 times 10 to the 15th hertz are incident on an aluminum surface. Work function for the aluminum is 4.08 electron volts. Find the maximum kinetic energy of the electrons, range of frequency for which no electron is ejected, and also find the voltage necessary to completely stop the photoelectrons current. First, let's find out what the cutoff frequency for the surface of aluminum is. The equation that I can use is phi equals to h times f cutoff. The work function is 4.08 electron volts, but I have to convert it into joules first. So I multiply it by 1.6 times 10 to the negative 19th. That's the conversion factor if you want to go from electron volts into joules. So that is going to be the work function in joules. And then I set it equal to h times cutoff frequency. So cutoff frequency is going to be phi divided by h. That's h. This is the work function expressed in joules. And I'm going to get the cutoff frequency to be 9.85 times 10 to the 14th. That basically tells you that any frequency lower than that is not going to be able to create any photoelectron. So when it says what is the range of frequencies for which no electron is ejected, is going to be from 4 times 10 to the 14th from this to 9.85 times 10 to the 14th. Any frequency in this range is not going to create any photoelectron. Any frequency higher than that is going to create photoelectrons. Now, in order to find the maximum kinetic energy, you have to basically use those photons with maximum energy, which is going to be these, and then you can say maximum energy for the photoelectrons is going to be hf minus phi. H is this, maximum possible frequency is this, minus the work function, and you're going to get 4.58 times 10 to the negative 18th joules. That you can then go ahead and convert it back to electron volts by dividing this guy by 1.6 times 10 to the negative 19th coulombs. And then that's basically the answer for the kinetic energy. And then you want to find the voltage necessary to stop. I told you that maximum kinetic energy is E times the stopping voltage. That's basically coming from the conservation of energy. And that means you have to divide this number by E, which is going to give you the same value. So 28.6 volts is the stopping voltage. I was going to actually go ahead a little bit more, but I'm out of time. That's something that I will make a video of, and I put it on Blackboard. Let me tell you that before we finish this lecture, since I have to make that video, you probably will have access to the folder for the next lecture a little bit later today. It's going to be probably around 2 or 2:30. I have a meeting with some of you guys this afternoon as well. I also wanted to ask you to go ahead and fill out the evaluation forms. that we have for this course. You probably have received emails, and they keep emailing you to do that. So go ahead and fill out those evaluations as well. If you have any question, please let me know. Otherwise, I will see you all on Friday at 10 o'clock. Thank you very much. If you don't have any question, I'm going to end this lecture.
What's the E?
E is the charge of the electron.
Okay, so that's another fundamental constant.
Yes, it's 1.6 times 10 to the negative 19. That's the same value that we have here.
Okay.
That's charge of the electron. That's the same. Basically, the charge of the electron and this conversion factor that we go from joules to electron volts or vice versa are the same. That's a good question. Any other questions? Okay, well, thank you very much. I'm stopping this lecture, and